And so the last talk will tell us about parallelization of the Kalman-Filter, and speakers and well.
So thank Heather for giving a great introduction to this talk this morning. This stuff you already know. We've got more luminosity, and we've got lots of cores that aren't getting individually faster all that much. So this project is looking at parallelizing, vectorizing Kalman-Filter. Well, why are we doing that, and what's it for? Well, you heard about Kalman-Filter this morning. It's basically a way of producing a estimate of a track that is in some sense optimal. Basically by adding new information as you populate the track through the detector. And why is it for tracking? Because it gives you robust handling of multiple scattering, energy loss, and material effects. It's widely used. We've spent decades understanding its problem. So our goals is to try and make effective use of parallel and vector architectures, Kalman-Filter, maintain the physics performance. That means, in particular, we want to try and maintain consistent systematics across platforms. We want to be able to make opportunistic use of different kinds of unconventional architectures, which may be overly ambitious. We'll see. So the basics of track building. You start from a set of seeds, and finding seeds is out of scope for us. We looked at it a little and decided that there are a lot of other people who've got better ideas there, and so we're not working on that. Once you've got your seed, you propagate it, you get an estimate of the track parameters, you propagate the next layer. In a classic road search track finder, you look for hits near that projection, evaluate each of those hits as a candidate for adding on, and select the best combinations, update your track parameters from those combinations, and then iterate onto the next layer. So the challenges here, well, first to get good efficiency, you have to look at multiple hypotheses, because what you get as the best local hit to add to a track may not be really globally the best. And if you've got a dense detector, a lot of hit candidates, you may have to look at half a dozen or so different hypotheses all the way through the detector. And then there are multiple branch points in this. That you have to select candidate hits each layer, evaluate a variable number of track candidates, select the best combinations, and so a lot of seeds, especially if your seeding algorithm is generous, are going to die out after a few layers. And all these branch points means you've got an irregular workload, and that makes vectorization and parallelization hard. So what we have done so far, what we're working on, so we decided to start out with a very simple approach, just to understand what we're doing. So start out with, at the time, what was available was Knight's Corner, and a comparison reference Xeon. Start with just a simple cylindrical geometry, lots of tracks uniformly distributed so that you don't have the worst part of the workload distribution problems. Start out with track seeds from Monte Carlo Truth. Start with track fittings and warm-up exercise. And just use these things to develop the measurement and validation tools, understand the techniques, develop intuition about how these things work, and then move on to adding complications like realistic geometries, realistic events, realistic seeds, and additional platforms like Knight's Landing and GPUs. So one thing we did early on was decide on developing our own data structure for doing the matrix multiplications. We didn't find anything that really matched the requirements of lots of multiplications of relatively small vectors. in an efficient way, at least for our problem. And so this is a matrix major representation where you're going first element of the first matrix, first element of the second matrix, and so on in the fast direction. We use a unit vector width on the Xeons and the Xeon Phis. We have generation code that can generate these at various vector widths. The full vector width, we can generate intrinsics and do various optimizations like knowing which things have to be zeros. And then for GPUs, I'll talk about this more, but we end up using the same layout with much larger vector width. And then we template these things so that we can use a lot of the same low-level code between the Xeon Phis and the GPUs. So the quick results from starting simple, these results are from a 61-core Xeon Knight's Corner. And on this processor, you can only actually need 122 threads to utilize all the clocks because it has to switch back and forth. And then a 16 single precision float vector width. And the top plot here is our parallel speed up on the very simple problem. And you can see we're pretty close to ideal up to the number of cores. And then it starts to flatten out because of resource contention in the cores. And ideally, you'd get up to around 122. But it's passable. And then for the parallelization, what we end up using is Intel threading building blocks. I'll say a little more about that, but we found it worked better than OpenMP for us. And for vectorization, you can see for the track fitting, we're getting about half the full potential vector speed up, which means about half our code is vectorizing well. And then for the track building, it's and I'll talk a little bit more about that later. And the lessons we learned from this, from the exercise of doing things simple, first, everybody who's ever done track building knows their coordinate system matters. And we had to play around a bit with different coordinate systems. It found one that we could vectorize well, but also gave us decent physics performance. And we ended up, I have an illustration here, what happens if you make a poor choice of a coordinate system. And we ended up one where the spatial coordinates are Cartesian and the polar and momentum coordinates are polar. And then on the computing side, I mean, these are mostly obvious lessons. You need to keep your data structures and memory allocations minimal. The data locality is critical. These machines, the Knight's Corners and Knight's Landings have fairly strange memory architectures, and you have to understand how that interacts with your data access patterns. We found that one way of effectively dealing with a lot of the work distribution issues was to use threading building blocks with work stealing. And as long as we found the right balance between too little and too small task sizes, this could even out a lot of the tail effects, where you get some tasks finishing before others do. And then paying attention to the vectorization reports. We used the Intel compiler for most of this. The Intel compiler is extremely detailed vectorization reports, and it can tell you a lot about why your code is not vectorizing. Particularly about unaligned accesses, type conversions. And we also found there are a lot of places where we needed to give the compiler hints about prefetching or using intrinsics for scatter gather instructions. And then generally using const and minimizing split variables helps give the compiler hints. So we're now at the phase of adding complications. That means a realistic detector geometry with end caps and transition regions. And these things have complex geometries, which can choose memory pressure. And take time to navigate. We want realistic events, which means they may have lower occupancy or higher occupancy, and less uniform distribution, which means new issues with work distribution. And then adding Knight's Landing, which is a lot like Knight's Corner, but has got some of its own quirks in memory organization and the microarchitecture. And then looking at GPUs and seeing how well we can adapt our code And so this is work in progress. So the rest of the talk is going to be kind of just, here's where we are. And so on realistic geometry, we've got two things in progress. One is still a kind of idealized geometry that's a cylinder with lids. And this is basically a tool for developing algorithms for handling end caps and transition regions. And then a real CMS geometry. And what we're trying to do here is find out what approximations, what shortcuts can we take that will let us use a realistic geometry that still vectorize well and avoid dealing with all the complications of the real CMS geometry. And so one trick is that we propagate tracks to the average radius of the layer. We don't figure out what the real radius is at that point. We take an average radius. We blow up the search window when we look for hits, and then propagate to each hit location. And the advantage of this is first, we can make it work with simplified geometry, which saves us a lot of pain, and we can vectorize this very well. And so we're still working on the transition region, and we're doing physics validation first before we do performance studies. And so right now we're working on verifying that we can do as well as the CMS tracker does. Compensating for variable occupancy, CMS events can have a lot fewer tracks or a lot more, especially when we're dealing with seeds from the iterative track finder, which has got its own quirks. And so that lower occupancy can cause difficulties for keeping the processors busy. And so the one solution for that is to keep multiple events in flight. In fact, the CMS framework already does this. And one advantage of doing this is that when you've got varying levels of parallelism in different tasks, they can fill in for each other. And this is another place where TDD works really well. And you don't have to worry about trying to schedule that yourself as long as your task size is about right. But there's still scaling limits when you do this because now you've got data structures per event, like things like how are you finding the hits in this event? You've got to replicate that for all the events, and so it still introduces scaling issues. And so there's still work we're doing here. And at really low occupancy, we find that KD trees can be effective instead of using the kind of that we use for high occupancy. And then moving on to what we've been doing on the GPU work, we ended up, after trying a few different things, using the same kind of layout as we used for the Xeon Phis, that we found it gave better performance than some of the other obvious alternatives. And it also meant that we could template the GPU and Xeon Phi versions with the same interfaces, and that meant we could have the low-level routines, like propagation routines and everything, common templates with just the steering logic different. And then for handling branching in the GPUs, what the scheme we came up with is that we say we're going to have this many candidates for each seed, and we have a fixed allocation of those. So you don't have to reallocate things as you go along, except if you may occasionally decide, oh, so many things have died out that I need to repack this structure. But for the most part, you just keep a fixed allocation, and that includes a fixed allocation for your additional hit candidates. And then what this figure over here shows, that you can't see by now, is that we heap sort this thing so that we can keep this a fixed size and still always know here's the next candidate, here's the worst candidate we found so far. If we find a better one, we'll toss that one out and add a new one and do that in a deterministic time that you can do in a GPU. And then about out of time. Going back to the track building vectorization, what we're looking at now is that we know from looking at CPU profiling and VTunes and the like, that part of the reason our track building vectorization is so poor is because we're spending too much time moving things around. copying things from place to place. And the other place where we're losing time is finding the hits that we want to add on the next layer. And so for the first things, just copying things around, we're looking at copying the GPU approach. We just allocate, you say, we're going to use this many locations in our vector registers for this seed, and we're just going to keep doing that. We're not going to copy stuff in and out. Again, a whole bunch of stuff died out, then maybe we'll repack at that point. But if we can, get our vector registers half full and get rid of most of the serial code, then that's a win for us. So because right now we're spending too much time trying to get our vector registers full, and all that bookkeeping and keeping them full is killing us. And the other thing, I'm not going to go into this in detail because it's kind of complicated, but the search for hits, you can actually turn that inside out. If you know that all your hits and all the tracks in your vector register are going in roughly the same direction, you can find the union of the hit candidates for all of them, and then evaluate all of them as a vector operation where you have everyone look at every hit. And if you don't know where the tracks in the vector register are going, then that doesn't do you any good. But if you know they're all going to have roughly the same set of candidate hits, then turning that inside out, while it may seem non-intuitive, can actually vectorize quite well. And so our perspective so far, we think our simple plan is working for us. We got fairly good parallelization on Knight's Corner using our simple case, and so far we're finding that translates well to the more complex cases. The vectorization is more of a challenge, and so we're still working on that. We're close to having the realistic geometry and events nearing completion. We've got the track validation infrastructure that's telling us that we're doing about as well as the CMS tracker and the barrel and the end caps, but we still have the transition region to do. And we're making progress on the GPU front. And one thing we learned from this is that I think we've actually benefited a lot from trying out different architectures. That the things we tried out in one architecture sometimes told us things that we should be trying on the other architectures. And I think we have a decent prospect of having both the GPU and Xeon Phi versions that share a lot of low-level code. Questions?
Why many 6 by 16? I'm not very familiar.
It's because that's all the Kalman-Filter math is. It's you're taking a track state that's 6 vector. It's 3 spatial and 3 momentum coordinates, and propagating into the next layer. You've got Jacobian, it's a cross product of those. That's a 6 by 6. And everything in the propagation is taking those 6 coordinates and multiplying by 6 by 6.
I just wondering about the 6.
Yeah.
Other questions?
You mentioned the GP flat over to share code between the CUDA and the...
Yes. So that was the G-Plex is the GPU version of the matriplex structure. So that's the things that share our templated structures between the two.
Writing and hard to connect the...
Yes. Yeah.
Other questions? Well, now let's thank the speaker and all the speakers.